Yes, the other way in which we can use gravitational waves to probe cosmology is to use directly the gravitational wave emission from binaries to probe the late time dynamics and the content of the universe. Okay, so I will try in this talk to explain how LISA can help in both with both probes. And here you have a cartoon that summarizes the sources that one can observe in LISA. So the green line here, it is the LISA sensitivity and strain as a function of frequency. And here you see the highest SNR, the highest signal to noise ratio sources, which are massive black hole binaries that LISA will observe. We have here all other kind of binaries which are almost monochromatic, which are the binaries, white dwarf binaries in the galaxies, or neutron star binaries in the galaxies. There are then these lines here that represent stellar origin black hole binaries of the kinds that have been observed by LIGO and Virgo already today, that can that LISA can pick up during their Inspiral phase. And then we have now here the harmonics of some MRIs, and this could be some possible stochastic background from the early universe, and this is the stochastic background from galactic binaries. So as you will see, all these sources more or less can be used to perform cosmological tests. Okay, so 2 words on LISA. As you know, it is going to be interferometers with 3 arms that is going to fly on an heliocentric orbit following the Earth, and participants can now see your application. Do you see my screen? Is everything okay?
So Chiara, we see everything fine.
Okay, sorry. Okay, so the frequency range of detection of LISA is from 10 to the minus 4 Hertz up to 1 Hertz, more or less. And okay, this is basically a bit more about the structure. So each spacecraft has 2 masses in free fall, and the lasers are sent from one mass to the other, and then another laser, after being phase locked, is sent back. And LISA will, it is actually a survey instrument, so there is no pointing. LISA will perform revolution around the sun with a continuous sky observation. Okay, so what it measures obviously is the strain. Okay, so the difference in the length of these 2 arms due to the presence of the gravitational waves, if one is able to reduce all the noises. And the targets, as I already explained, there are several kind of sources with these different masses and different mass ratio. And then what can also observe LISA is a stochastic background of gravitational waves, which is some kind of noise. So there won't be this kind of very well-defined waveform, but some white noise, which could be due either to astrophysical sources, so binaries that are too numerous and too low, with too low signal to noise ratio to be individually resolved, or LISA could also pick up a background signal from the early universe, which in this case it is a background because the correlation scale typical of this background is too small with respect to the detector resolution to be able to resolve this kind of signal, and so it also appears as a noise. And in this case, the observable which is usually used is the energy density of this noise and its power spectrum. Okay, so let me then go to more in detail what LISA can do concerning the early universe, and in this case is exactly this observable that we are dealing with. Okay, so in this cartoon, here we have a cartoon of the early phases of the universe evolution, and what the message I want to convey is just that you know, in principle, we have observed cosmology or tested cosmology up more or less to the BBN scale, plus through a CMB anisotropy, obviously inflation. We have tested physics more or less up to the TeV, right? And actually, gravitational wave sources are propagate freely since basically the beginning or the phase of inflation. Okay, so if we have gravitational wave sources that operate somewhere at inflation or up to, let's say, the BBN scale, this would allow us to get some information about the new physics that generates these gravitational waves, or even probe physics that we have already tested. So it has a very big potential. The gravitational waves have a very big potential to test the early universe. And here with this cartoon, I want to convey the same message. Okay, but here, as you can see, so there is this possibly wide range of scales between inflation and BBN, on which we could gather information using gravitational waves. And as you can remark here, I put some connection between some gravitational waves observatories, Earth-based, LISA, PTA, and energy scales in the early universe. So now I will demonstrate how to do that. And I also want to point out that in this wide range of scales, we do expect very interesting phenomena to arise: reheating after inflation, baryogenesis, phase transition, dark matter candidates, on which we don't have direct access with the electromagnetic radiation, with photons. So it is important to use gravitational waves for that. Okay, so in the universe in general, we insert gravitational waves as tensor perturbations of the metric. Okay, and we have two possibilities. Either we consider a phase of inflation, and therefore we don't need any source to generate a stochastic gravitational wave background, because it is going to be the fact that the tensor mode is not conformally coupled to the metric, and if the metric is background metric is expanding, then we have amplification of vacuum metric fluctuation. Okay, but this is a way of generating a background of gravitational waves, which is typical just of inflation, but we could also have the presence of active gravitational wave sources in the early universe. And in this case, what we are looking for is some tensor anisotropic stress, which is going to be the tensor component of this perturbed energy momentum tensor in the universe. Okay, so we need to find sources of anisotropies, tensor anisotropies in the universe, and high enough to be detected. So usually this guy, we are used to see this as the order of 10 to the minus 5, you know, in CMB anisotropies. Here, as we will see, we are looking for something pretty higher in order for it to be detectable. Now, if we consider then this active gravitational wave source, there is a particular constraint on its on the peculiar frequency, characteristic frequency that can be generated of the gravitational waves, because obviously we are talking about an active source that must respect causality, and therefore, if we look at the characteristic length or time scale of the source, which is going to be the typical size or time scale of these tensor anisotropic stresses, it is bound by the Hubble scale. Okay, and we expect that the characteristic frequency of the gravitational wave signal is nothing but the inverse of this characteristic length scale, and therefore it must be larger than the Hubble scale at the moment at which the source is operating. And then one can take this simple relation and redshift it to find the frequency today as a function of this particular parameter. Okay, so the size of the anisotropic stresses with respect to the Hubble scale, and the temperature at which, or energy scale at which the particular gravitational wave source is operating. Okay, and then this particular formula allows me to draw this kind of plots in which here you have the frequency of the gravitational waves today and the temperature or the energy scale at which the source is operating. That formula is the black line, you see. And if we look obviously at usual cosmological probes like larger structure, CMB, big bang nucleosynthesis, they explore low frequencies, correspondingly low energy scales, while gravitational wave observatories have access to frequencies which are in general much higher, and therefore, you know, correspondingly they open up here access to big high energy scales in the early universe. And in particular, so now making some reasonable assumption on the value of this parameter that appears here at the denominator, one can, for example, connect the frequency range of LISA, which is about a millihertz, to some epoch in the early universe, and this is around the electric scale. So this is what I was doing in the previous cartoon. Okay, so we can connect the frequency range of different observatories to you know, energy scales in the early universe that they can in principle probe. Okay, so here is another cartoon with the gravitational wave energy density as a function of frequency today. And here we see existing bounds or sensitivities of different detectors. We have pulsar timing arrays with you know, the recent noise excess that has been measured at this level. We have here LISA in the millihertz range, the CEICO, Earth-based observatories, present and future, and we have the CMB integrated bounds from the CMB and big bang nucleosynthesis. We have the bound at very low frequency by Planck, because the cosmic microwave background, you know, always put constraints on large scales. And then we have the LightBird forecasted bound. So in principle, then we can use whatever new physics to populate this diagram with signals. And in particular, we will see what we can do in the LISA frequency range. Okay, so let me give a few examples. Okay, very simplified. It is a very simplified discussion what I'm giving here. So, but it gives an overview. Okay, let's start with inflation. Okay, what can we do with LISA? Obviously, not much if we are in the context of standard slow roll inflation. Okay, because we already have a bound on the energy scale of inflation, and it is low enough not to be directly observed by any gravitational wave observatory. However, you see what is the potential here of these gravitational wave observatories, which is that they, you know, in principle allowed to probe the gravitational wave spectrum from inflation, and therefore the inflationary potential at very, very tiny scales with respect to what we are usually used, you know, using the CMB. So here one can very well consider that one is beyond slow roll, and you know, unconstrained phenomena can happen that can enhance this tail and make it, you know, pass through some of the gravitational wave observatories. And typically this is done by inserting, okay, either modifying gravity or inserting some active source during inflation, okay. Or also adding a phase with the stiff equation of state as well. So let's suppose that we just, this is the typical signal from inflation with the transfer function and the spectral index. Let us suppose that we free the relation between the spectral index at slow roll that forecast that this is very small and negative. And let's suppose that we have whatever for this, and then this is basically what Lisa can constrain in this parameter space between R, so tensor to scalar ratio, and NT. It is pretty trivial, as you can see. Let me just give one example of a model that it is nowadays quite constrained, but I find in any case interesting, which is, if we have this kind of coupling between some either a pseudoscalar inflaton directly or some spectator field during inflation, with the electromagnetic field, and then this can act as a source here, extra source of gravitational waves that would enhance. Here one would have the flat or almost flat spectrum would be enhanced, and it is a scenario that can be probed at LISA. Other very interesting scenarios that can be probed at LISA that have to do with inflation is whether, if inflation actually, so if one admits that scalar perturbation are actually high at these tiny scales, and one can have at the same time the production of primordial black holes and secondary gravitational wave produced at second order by the scalar perturbations, and therefore, and in this case, one can have this very nice synergy between, what one could observe in LISA from this background of second order gravitational waves, and what and the production of primordial black holes accounting for the totality of dark matter. Okay, let me now go, a bit down in energy scale and suppose that we are at grand unification energy scale. So maybe there are some phase transitions that can produce topological defects. Okay, and this is also a source which is very much studied in the context of gravitational waves, and in particular, it has been possible to infer very interesting constraints on, in particular, non-Bugoto cosmic strings with LIGO and Virgo. So let me, a caveat here is that the gravitational wave signal from this kind of objects is extremely model dependent. And in general, what is assumed is that these are non-Bugoto strings that give an quite important production of gravitational waves. And let me just flash what Lisa is able to do in this context, which is, providing very tight constraint on this G mu parameter, which is basically the energy scale of the phase transition, which is producing these cosmic strings of the order of 10 to the minus 17 for Lisa. Okay, and then I will sketch my favorite gravitational waves source for Lisa, which is an hypothetical first order electric phase transition. Okay, so I'm going down in energy scale yet again, and we are now around the TeV to 100 GeV energy scale. So there, it is the scale of the electroweak symmetry breaking. So in general, one can have, so phase transition can be of second order or crossovers, or at first order. And at first order, it means that there is a barrier that is developing here between the false vacuum and the true vacuum. Okay, while in second order transition, the order parameter is transitioning smoothly as the temperature decreases. Now we know that in the standard model of particle physics, there is no gravitational wave production because we are in this scenario. So the electroweak symmetry breaking is a crossover. Okay, so we don't expect any gravitational wave signal in the context of the standard model. But if one invokes some beyond standard model beyond standard model physics, okay, one can open up the possibility that the electric symmetry breaking is of first order, and one can have the production of gravitational waves. And this is, in my opinion, a very strong scientific case for LISA, because there are a plethora of scenarios that were there even before, that were proposing to have a first order electric phase transition even before realizing that they actually give rise to gravitational waves, because this is something which is interesting in itself from the point of view of particle physics. So what happens basically? Why do we have a gravitational wave production in the case of first order phase transition? Because the fact that the scalar field must overcome the barrier either by thermal fluctuation or by quantum tunneling corresponds to the generation of bubbles in the true space. In real space, bubbles of the true vacuum. And these bubbles very quickly expand because the phase is energetically favored and collide. And it is exactly the collision of this bubble that produces an active source of gravitational waves, the type I've already been talking about. And in particular, there is directly the fact that, these bubble walls are gradients of the scalar field, and therefore, they have in general tensor component at collision because spherical symmetry is broken. Then we also have the fact that in general, the scalar field, for example, the X field is coupled to the surrounding fluid. And when the bubble wall is set into motion, when the bubble wall expands, sets the surrounding fluid into motion, okay, generating possibly turbulence, certainly sound waves in the fluid that also have a tensor component. And this fluid motion can be accompanied actually by primordial magnetic fields because the fluid is fully ionized. And so in general, we expect magnetohydrodynamic turbulence. And electromagnetic field has a tensor component by itself in its energy momentum tensor. So you see how rich is the phenomenology that can give rise to gravitational waves at the first order phase transition. And as I stressed already a couple of times, in the case of LISA, it is really the electric scale which is relevant. Okay, so here you have just an example of a signal, omega gravitational waves as a function of frequency. The red line is the LISA sensitivity, and the black line is the expected signal in one particular beyond standard model scenario. Okay, and here you recognize a peak in the spectrum that corresponds to the typical scale of the anisotropic stresses, which is now obviously the scale of the bubbles. Okay, so just one example to flash that we can actually observe something in LISA if one of these scenarios is realized. And here okay, I just want to convey the message that actually there are very important connections that can be established between what can be probed with LISA and other kind of observable, like baryon asymmetry, the presence of dark matter candidates. And so we can see LISA, as probing beyond standard model physics in a way which is complementary to particle colliders. And here you see for the same model I was showing you before, right? So, in the parameter space of the phase transition, strength and duration, dots that can be probed by LISA and at the same time by the LHC. Okay, and let me just advertise that there is this particular web tool that we have developed within the cosmology working group of LISA, which can, if you have your favorite phase transition model, provides you with spectrum and observability. Okay, so this I can skip. Okay, so let me now summarize this part concerning the early universe. Okay, so we have seen signals from inflation, and particularly interesting for LISA, in my opinion, is this connection with primordial black holes, possible connection with primordial black holes. I have then briefly discussed cosmic strings and flashed that LISA can provide actually good constraints on the string tension. And then I have explained a bit more in detail the electric phase transition and its potential to be tested by LISA. So the bottom line, as far as I'm concerned, is the stochastic gravitational background from the primordial universe might seem speculative, but their potential to probe fundamental physics is great, and amazing discoveries can be around the corner. Okay, so both obviously more concerning present interferometers, Earth-based interferometers, but also with LISA, it has a great potential to provide, complementary constraints on what can be done with Earth-based interferometers. Now, the important point is that one must improve data analysis techniques in order to be able to distinguish these particular signals that are in the form of extra noise from all the rest. Okay, and now I will briefly go through to the second part, which is, the use of gravitational wave emission from binaries to probe the late time dynamics and the content of the universe, always with a special focus on LISA. Okay, so as you all know, right, what we would like to probe, so okay, or let's say one of the probes of the content of the universe is testing its background expansion, and in this case one observable is the luminosity distance as a function of redshift, because obviously this provides access to the Hubble factor and therefore to the cosmological parameters, or directly at low redshift to directly H naught today. Okay, and as you all know, and I'm sure you have been discussing in this workshop, there is this tension nowadays between different probes of the Hubble factor today, and these probes are, early universe and late universe, but more or less based on the electromagnetic waves. And it is possible to hope, let's say, that gravitational waves, being a different messenger, could provide some new information in order to address this tension. Now, how to probe this luminosity distance versus redshift relation? Obviously, with supernovae, for which it is very easy to get the measurement of the redshift, okay? But what is a bit more difficult is to get the measurement of the luminosity distance, because you need to calibrate the supernovae to sources that are closest, like say fates, etc. So it is not a direct measurement that you obtain of the luminosity distance, but you measure actually the flux. Now, for gravitational waves, okay, if we use gravitational wave binaries as what is called standard sirens, the situation is actually converse, in the sense that the measurement of the luminosity distance is easy and direct and doesn't require any calibration. But the measurement of the redshift is actually absolutely impossible, right? So, why? let's see. So here we have the strain, gravitational wave amplitude, let's say, in the two polarization modes, in the, order 0, let's say, in the Newtonian expansion, Newtonian approximation, sorry. And basically what you have is that the amplitude goes down like 1/r, and if you put your source at a cosmological distance, you have the expansion factor times r. Okay, so this is the propagation effect at the observer. Now, you want also the signal at the observer. And if you do that, you actually see that the waveform is transformed in such a way that there is a complete degeneracy. What is the denominator here becomes the luminosity distance, but the mass becomes the chirp redshifted chirp mass instead of the chirp mass. And so the redshift and the true chirp mass are fully degenerate, and it is impossible to disentangle them with gravitational measurement uniquely. And here, okay, this is just to show how one gets instead a very direct measurement of the luminosity distance. And this is simply because basically you get the chirp mass from the waveform. And then if you are able to measure the two polarization modes, then you get the luminosity distance very neatly with the gravitational wave observation. Now, the full question is, how can we break this degeneracy between the redshift and the true chirp mass and use gravitational wave emission to build the Hubble diagram? Okay, so there are a few methods to obtain the redshift information that depend on the nature of the source and of the detector. But bottom line is that in general, one needs to invoke some electromagnetic measurement to be able to break this degeneracy. So one can directly do it by identifying the galaxy which is hosting the gravitational wave merger, or identify the galaxy, so you measure directly the redshift of the galaxy, or you measure a transient counterpart directly connected to the merger. On the other hand, you can suppose that you have a lot of gravitational wave sources and you try to cross-correlate the sky position sorry, I got lost because I have my Skype open and I hear pling pling. Sorry about that. So you can actually cross-correlate the sky position of the gravitational wave events with galaxy catalogs. Okay, and therefore, with this way, we hope to statistically identify the host galaxy and therefore have a measurement of the redshift of the gravitational wave event. Another possibility is to assume that one knows or constrains the intrinsic mass of the object. This is always possible, and in this case, you can do it fully with gravitational waves without the need to introduce any electromagnetic counterpart. Okay, and this can be done, for example, using neutron star by assuming that you know what is the typical mass of a neutron star because you have a physical prior on the mass of this object. Now, let's focus for a moment on the direct method, because here there is a difference between what can be done with Earth-based interferometers and LISA. Okay, so with Earth-based interferometers, we have seen it how occurring. One gets counterparts from neutron star binaries. Okay, possibly neutron star black hole binaries, but instead for LISA, the sources that are the most promising with expected counterpart are massive black hole binaries that occur at the center of galaxies. These are the highest signal to noise ratio sources for LISA. concerning the statistical method, one cannot, it's challenging to use massive black hole binaries because they are not very numerous in LISA. We don't expect to observe thousands of them. And for the statistical method, you need to have a lot of sources because when you cross-correlate with these galaxy catalogs, the galaxy catalogs are incomplete. They are bound in redshift. And in general, the sky position that you can get out of the gravitational wave parameter estimation, so the sky position of the gravitational wave source, as we have seen already with LIGO Virgo, is very bad, and therefore in general you have many galaxies in a sky position box, and therefore basically it is extremely challenging to perform this statistical method, and you need a lot of gravitational wave sources to beat down the error statistically. Okay, and in general, so with Earth-based interferometers, this method can be used, okay, with stellar mass black hole binaries or neutron star binaries, but with LISA, you know, basically the only sources that can be used for the statistical method are extreme mass ratio inspirals. Okay, the rates of extreme mass ratio spiral is not very well constrained yet, but they could indeed be very numerous. Okay, so let me just focus, I'm almost done. Let me just focus specifically now, give some results about LISA. So first of all, concerning the direct method. So using massive black hole binary mergers, okay, so the counterpart is expected, you know, the most, so we are actually studying this right now, but it seems that the most favorite one is the radio emission that can be associated with a flare at the merger, okay, possibly followed, so but with the radio emission, obviously you don't get the redshift, you just use it to localize the source. And then you, when you have a very good localization of the source, you try to get an optical identification of the host galaxy. Obviously, one needs to select events with high SNR and good sky localization, and one needs to account for the fact that weak lensing strongly affects the measurement of the luminosity distance. So here in this cartoon, you have as a function of redshift some histogram of a distribution of standard sirens. So you see that they peak at quite high redshift, you know, between redshift 2 and 4. Here you have a reconstruction, obviously, it's all simulated data, a reconstruction of the luminosity distance versus redshift diagram with this kind of standard sirens, okay? And you see here as well that they sort of cluster between 2 and 4. And from this paper here, these are some forecasts on what LISA could do using this kind of sources, massive black hole mergers on H0. Okay, it's basically the uncertainty on H0 strongly depends on the number of available standard sirens, which is not huge, as I was saying before, and it is of the order of %. Now, I just want to flash that these kind of sources has also been invoked to test modified gravity theories. In particular, this particular theory has been pointed out in this paper. Okay, and now a couple of words on the statistical method with LISA. So using MRIs. Okay, so one could also imagine, why not using stellar origin black hole binaries? Well, unfortunately, they are too rare for this statistical method in LISA. But MRIs can be used for cosmology, as has been demonstrated by this paper, if we use a subset of MRIs that have a pretty high signal-to-noise ratio. And you see that in this case as well, we as pointed out, derived by this paper, the typical constraint on H0 is of the order of the 3%. Okay, so I've come to the end. So here is just some summary of the second part of standard science. Okay, so basically LISA can provide, as we have seen, some percent measurement of H0. It is possible that this forecast is going to be improved. Actually, we are right now revisiting massive black hole binaries as standard science. So stay tuned for new results. Actually, but what is important for LISA is that actually this particular what differentiates LISA from other probes is that these sources, as I have pointed out, they cluster a pretty high redshift. So they could provide some complementary constraints to the expansion of the universe at high redshift. Okay, so thank you very much. I'm done.
Thanks a lot to Chiara for this very nice talk. I think Diego was the first.
Hello, can you hear me, Chiara?
Hello. Hi, Diego.
We can see you huge now in the screen.
Yeah.
It's a bit intimidating.
Oh no, I will share screen again. Sorry.
Eh?
I will share my screen again so you see the slides.
Yeah, I wanted to ask you something about the last point, the last part. Is there any hope that by using some kind of nonlinear physics of the gravity waves to break this degeneracy? Because in the end, I don't know if these formulas that you are putting in are kind of linear theory, for emission of gravity waves, and also in the same. We had a talk before about these memory effects. I even wonder if people have explored whether this can be used for breaking this degeneracy.
Yeah,
and also going beyond optical approximation, maybe to break this degeneracy. Maybe these 3 points. Yeah, thank you.
Yeah, okay, this is all possible. I cannot say much because I haven't done the studies by myself. What I have been studying is to go beyond the assumption that the redshift is constant. Okay, so because here you are obviously assuming that the redshift is a constant, but in general, the redshift, so imagine that, during the redshift can vary in the sense that, for example, during the time you observe the binary, the universe expands. Okay, and in this case, you could have some effects that come, that allow to break the degeneracy. But the problem is, in this case, is that what dominates this perturbation in the redshift are cosmological perturbations of the matter structure, basically due to the matter structure, and in particular peculiar velocity. Okay, so the effect that is due to the universe expansion is absolutely subdominant with respect to the effect due to the fact that the source is moving by itself, and therefore this particular possibility of breaking this degeneracy does not help. It breaks the degeneracy, but it does not help to constrain cosmology. Now, there are for sure other possibilities. Now, it is always, it is always a problem to understand the magnitude of all these effects and whether they can actually picked up observationally. Sorry, it
okay.
wasn't, very precise answer with respect
Diego,
to...
you are satisfied, right? Okay. There is another question by Rom.
Regarding the constraints on cosmic strings, so when you put this constraint, do you assume gravitational radiation from the largest possible loops? Because typically that's the free parameter for cosmic strings, no?
Yes, yes. So these constraints is for large loops. Yes, yes, absolutely.
Okay. And do you have any idea what what will happen if you consider small loops, for example?
Yes. So I had there was a study, and I think the constraint degrades for small loops. I'm sorry, I don't have a backup slide here, but okay, I think the constraint on Gmu degrades for small loops, but I thought that it was nowadays more or less, there was more or less an agreement in the community that the loops were big, right?
I mean, it's typically due to the numerical simulation. I mean, most of the numerical simulations has a peak around alpha equals to 0.1. It's like
exactly
10% of the horizon. But if you do theoretical modeling, so alpha is basically a free parameter.
All right, all right. So, okay, so these constraints are for alpha of the order of 0.1, and the constraints degrade for alpha smaller.
Yeah, okay, thank you.
Are there any more questions? Are there any questions on Zoom? If not, maybe I will abuse my position and ask Chiara a question. So is there any particular study like by Lisa people on these constraints on domain walls, for example, or maybe other defects? Or it's only for strings?
No, no, not that I am aware of. People have used, in general, consider only strings because domain walls are unstable, right? You know that they cannot, I mean, if they are stable, they dominate the universe expansion. And so basically I think people think that they are more or less excluded.
Oh, that's very good, because we have a model when it's not the case, when they melting down.
Okay,
and the gravitational waves before.
Okay, so in this case, yeah, so certainly if you have domain walls, they do produce gravitational waves. There have been studies of how they actually influence the CMB, for example, and I think there are papers by Dani Figueroa where he evaluates the gravitational wave spectrum by, in general, defects and can be applied to domain walls as well. And so I think, you know, if you have a favorite model and using the spectra, it could be quite easy to find a background, I mean, a constraint by Lisa.
Okay, great. Thanks. I probably also write to Daniel then.
Yeah.
Perfect, thanks. Any more questions? Okay, if not, then let's thank Chiara for this very nice overview.
Thank you to you.